So yeah, hello everyone. I'm Dennis. I'm currently a PhD student at the University of Parma. And today, instead of talking about field level or class 1 loop, let's talk about multi-field inflation. And I think it's also the topic of today, more or less. So we're going to talk a little bit about the galaxy power spectrum, bispectrum constraints coming from specifically in Euclid, within the Euclid collaboration, what we're currently working on with all of these people, which most of them are also here. Okay, so first of all, I would like to also thank the organizers for the wonderful workshop and the conference here. I mean, Florence is of course amazing. So staying around here for such a long time is always a pleasure. So thanks very much. Now we can become a little bit more technical. So yeah, as it was already mentioned before, we have an intuitive picture what exactly local primordial non-Gaussianity is supposed to do at the level of the galaxy power spectrum, but also the bispectrum. So what we basically do, if we focus now on local non-Gaussianity, what we have is basically a Gaussian potential, and now the non-gaussian field on top of it at the level of the potential. At the level of the density on itself, it was shown that we have a scale-dependent bias, mainly coming from the FNL phi loop, and this is a nice demonstration at the level of the power spectrum, so this large-scale signal, which is enhancing clustering on larger scales. On top of it, you can also imagine that we have here cross-correlations, also loop effects, which are also rather important at the level of the power spectrum. And on top of it, that it was also mentioned at the level of the bispectrum. So there's a lot of signal coming on different channels, which we try to test out. Okay, so to put everything in perspective, as it was already shown, and most of you of course know, the current constraints we have mostly coming from Planck, which is already pretty good with an error of ±5. And SDSS, a lot of people were working on where we have ±20. And in DAISY, current results coming to approximately 9. Of course, we want to push it to order 1, as it was shown before, to actually be predictable for most inflationary scenarios. Okay, so the question now is, how far can Euclid go approximately? So for that, we were developing together with Azadeh the pipeline, which is fully integrated into Cosmosis. So within Cosmosis, we have developed the G-class and G-stats modules, which can be integrated inside of Cosmosis, where you basically have a sampler, Boltzmann code of your choosing, and these modules with the likelihood together, fully integrated and pretty fast. So what does it include? We have the one-loop power spectrum, a tree-level bispectrum currently included in real space and retro space, including now FNL. Moreover, we have also implemented, similarly as Class PT and I think also PyBird, the FNL loops on top of it, and have investigated the PNG counter terms coming from these new loop corrections at the level of FNL. We have implemented that standard-wise with FFT log matrices, and we are computing the Gaussian covariance of P, P, BB on the fly. Okay, on top we have a couple of features to advertise even more. We have analytical marginalization and also the reconstruction of these parameters. Also, for the code to be integrated within Cosmosis, what is nice about it is you can choose whatever Boltzmann solver you want. You can even choose emulators, as we do, for example, in our pipeline, for example, the Baco emulator, and very fast samplers, since they're also developing, which is very fast. So currently what we have is 2 to 4 hours wall time for high resolution PNG runs. So P, B, and P plus B, since everything is parallelized with MPI and OpenMP. For fixed cosmology on top, you can run it on your laptop and it's more or less 2 minutes. Okay. So having said all that, what we were doing within the collaboration, and specifically the higher order working package, is to analyze the Abacus Summit. So the Abacus Summit itself is a rather small volume and low resolution, including FNL, and it only has 2 realizations. Nonetheless, it was sufficient for us to populate it now with Euclid-like H-alpha galaxies on top of it, which were basically matched to equal to the flagship ones. Okay, to the pipeline, we assume now Gaussian covariance. We vary cosmology to see the effect how opening up the FNL parameter space. enters into cosmology and what kind of scale cuts we actually are able to investigate. And we fix B phi delta and use a prior choice on B phi. So instead of fixing B phi, what we do is to use this common relationship and having now a physical prior on top of it. This prior is more or less, so we know if P equals 1, it's a universal halo mass function. On the other hand, we had also illustrious constraints, so where B phi was measured on illustrious and it was 0.55 measured for PB phi for different redshifts. So our agnostic approach was to say, okay, we have a prior choice, which basically meets itself in the middle. We don't know what exactly our sample size will be. And we include both of these models, if you will, within 1 sigma range. Okay, so this is now the power spectrum. We were analyzing 4 different redshifts to see exactly how it runs for the FNL30 simulations. So as you can see, on the one hand, these are different scale cuts. And we can see that our thing of bias for all the cosmological parameters is always below 1 sigma. So this is 1 sigma, this is the 2 sigma range. And we can push actually to very small scales, which was also rather surprising. Nonetheless, within the main analysis, we stick to 0.3. What we can see, moreover, is within the FNL and the thing of merit of FNL, that by going even by having the loop contributions, there is still too small for the covariance that we have to actually get information out of it, since it's mostly the large scale signal which we are here after. So basically by pushing to smaller scales, we can't get more constraining power coming from the power spectrum, but by going to higher redshifts, what we can see here, we have a factor of 3, moreover, better constraining power on FNL, which is expected. Okay, the same we also do for the bispectrum. So here again, different redshifts. And here we can see, of course, the model is breaking, right? So as you can see, for example, redshift 0.8 to 1.4, we can push to 0.12 H omega parsec to still stay within 1 to 2 sigma. So these scale cuts we can use. And for the highest redshift, we only push to 0.105 H omega parsec. And what we basically can see is the constraining power coming now only from the bispectrum only runs on FNL. And what we basically can see in here by going to actually smaller scales, what is happening is that we adding more squeezed bispectral triangles, right? And these carry still a lot of signal, which is improving the constraining power. So all of the modeling going inside of the bispectra to actually go to smaller scales allows us to include more triangles, which on top of it gives better constraining power on FNL. Again, we see an improvement by going to a higher redshift, as expected due to different scale lengths throughout time. Okay, so now what we basically do is to combine the constraints we had on P and B for the best scale cuts where we are within 1 sigma bounds of thing of bias. So this is now the highest redshift, 1.7, with the given scale cuts. And what we can see is the cosmology, we are pinpointing very nicely within the P only, B only, chosen with the scale cuts, but therefore also within the joint. And we recover FNL. So while we can see power spectrum is rather low, and that's a trend which we were seeing throughout all redshifts, bispectrum is mostly driving the constraints. So what we can see within that plot is a constraining power, which is the inverse relative error of FNL. And we can clearly see that the joint has more than 2 sigma detection for FNL30, in that case for our given volume for that snapshot. Exactly, so we recover basically a significant and unbiased detection of FNL30 within the joint. And as we can see specifically in that plot, it's mostly driven through the bispectrum, but the power spectrum, of course, also carries information. Then we have continued, basically going throughout all different redshifts. So 0.8, 1.1, 1.4, 1.7, which is closely related, of course, to the Euclid snapshots we will have in the end. And this is something we have seen before. So this is the multiples power spectrum, multiples bispectrum, multiple joint. On top of it, this shadowed region is if I only do the analysis with the power spectrum monopole, bispectrum monopole, and here I have the full multiples in the power spectrum and bispectrum monopole. And in turn, here I also have the quadrupole of the bispectrum. And we can clearly see the trend. So basically, if I mainly focus now on the joint, by including only the quadrupole, the bispectrum quadrupole, I still have a lot to gain, right? Well, main analysis coming from BOSS, typically you can see that the bispectra quadrupole is a little bit too noisy, but in our scenario, we had actual clean data to be able to measure something from it. On top of it, we have included now P slash and also B slash, which is basically a linear combination of the multiples. So I can recover my measurements of the multiples, combine them in such a manner that I can remove most of the velocity from it and recover mostly a real space analogous. One has to say it's not exactly a real space since there's still some residue in velocity. But the point is to see, okay, we do know how much RSD is able to break degeneracies in normal cosmology, lambda CDM cosmology rather to say, and the biases, but how does it look in FNL? And what we can see in the comparison of P only and B only, RSD is actually helping. So we have actual more information going to redshift space compared to only real space. Nonetheless, funnily enough, if I do a complete P plus B analysis in that slash space, FNL is not very improving. So it's more or less the same kind of constraining power. So this is now summarizing it. So on one hand, by going to a higher redshift, what we were seeing, we're consistently getting better constraining power, going from 1 sigma range within the joint to over 2 sigma range detection. We see that RSD helps with P only and B only constraints, but the joint is on equal terms approximately with and without RSD, which also gives a nice pathway and further investigations to see, since now by removing the velocities from your galaxy surveys, you can actually push to smaller scale cuts. And by pushing to smaller scales, as we were seeing, we can include more squeezed bispectra and get better, even better constraints on top of it. So let me summarize. I've presented our Cosmosis pipeline, which will be public soon and will be integrated fully within the supported Cosmosis standard libraries of the power spectrum and bispectrum, which includes the PNG. We have seen full scope analysis of the Abaku suit, which we have populated with Euclid-like galaxies to fit approximately flagship, and see the constraining power of given volume, which approximately, as I understand, resembles the R3 of Euclid. And we were able to see an unbiased significant detection of non-zero FNL. Of course, the value was now 30, so the question mark would be, okay, if it would be lower, how significant that detection can be. But by going to bigger and bigger volumes, of course, and as we are seeing in spherics, bigger volume has this bigger signal on top of it. So it's a nice pathway towards a non-zero detection with error bars tinier than 1. What is upcoming? Basically, we'll of course continue within Euclid to add systematics and service specifications. And we will in the end want to apply to DR1 to DR5. So DR1 is upcoming, as I understand, in a range of a year. And to analyze their FNL and see what Euclid is giving us compared specifically to DAISY and other surveys. And on top of it, we're currently working on other PNG shapes. So mainly equilateral and orthogonal, where we also want to include the power spectrum at 1 loop. This is a collaboration done by the group in Ferrara. So yeah, thank you very much for your attention. Mm-hmm. Mm-hmm. Yeah. Yes. Exactly.
Here, the larger is the bar, the better is the sensitivity.
Exactly.
Flash somehow sucks.
No, yeah, exactly. Exactly. So Kmax is fixed to only see what kind of information do I have compared to RSD, right? So I want to have a fair comparison. Exactly. So that's the, it's a fair comparison to say, is RSD breaking degeneracies for a given scale cut? So I put the same modes, the same information, and I just want to see, is there something more that RSD is resolving, right? But exactly the idea would be you want to push now. Yes. Exactly, exactly. So now the hope would be that I can push the bispectrum to, let's say, 0.2 or whatsoever, and then include a lot of more squeeze triangles and get even better constraints than what I was showing before. Yeah. Yeah. Exactly. So exactly what Azadeh was saying. So all of these plots have a huge appendix. So the monopole power spectrum, monopole bispectrum, and the P slash and B slash only runs are biased in AS, for example. So they recover FNL, but you're biased in cosmology, specifically AS. On the other hand, P's. Exactly. Nonetheless, yeah. But if I go here, exactly. So these are the actual chains behind it, right? And what you can see in first P slash and P naught, right? We're completely biased in AS, right? Nonetheless, everything is fine. Yeah. Nonetheless, here, that's exactly the plot. I can actually also recover the cosmological parameter in P slash and B slash space. So if you want, you can do the full analysis as it seems with P slash B slash only, push it to smaller scales. Of course, you have to determine your new scale cuts to see where this model again is breaking for your given covariance and volume, right? But what is nice is that you're actually on part on the FNL constraints, right? And both of them are giving you exactly the 30, which you want to expect. Came in for which one? For the power spectrum or bispectrum? Yes. So, okay. So basically we're doing the scale cut analysis in here, right? And here we decided to stick to 0.3. Came in. I'm sorry. Yes. Even for that I have a plot. Somewhere. Yes, here. So that's something we were also analyzing on top of it. So we also varied the K-min. So our volume is giving us a K fundamental, which is approximately 0.002 H omega parsec. And the question mark was, okay, if I remove these bins, the larger scale bins, where the signal lies mostly, exactly is what we see a drop in the thing of merit of FNL, right? So we need these larger scales, we need these larger spins to extract information, right? As expected. This is where the signal lies. But this is the volume we are considering here.
Okay, so let's thank Gary again. So,